Hello everybody. In this video, I want to talk about doing conversions for temperature values. And these are a little bit trickier than other conversions that we've done. The reason being is because the scales between the different units of temperature don't necessarily line up. So another way to say that would be like, for instance, if we're converting a foot to a meter, they're different units, but 0 feet is still the same value as 0 meters. But that's not necessarily true between, say, Fahrenheit and Celsius. 0 Fahrenheit is not the same as 0 Celsius. So to do these conversions, we have these formulas that account for that. So for instance, to convert to units of Celsius from units of Fahrenheit, we're going to first subtract 32. And this 32 value that seems to come out of nowhere is actually because 0 degrees Celsius is negative 32 degrees Fahrenheit. So we have to make that correction first. And then we multiply by a conversion factor, which in this case is 5/9, and that's because there are 5 degrees Celsius for every 9 degrees Fahrenheit. So this is kind of a conversion factor like we've used before. So if we look at an example of converting from Fahrenheit to Celsius, we have a warm summer day, has a high of 73.4 degrees Fahrenheit. What was the high in degrees Celsius? So we start off by plugging in our temperature value, 73.4 degrees Fahrenheit. We subtract from that 32 degrees Fahrenheit. I didn't write the unit up here because you'll often see it written that way, but it is degrees Fahrenheit. And then we'll multiply by our conversion factor, where we have 5 degrees Celsius for every 9 degrees Fahrenheit. If I do this math first inside the parentheses, I get 41.4 degrees Fahrenheit. I then do the conversion where I multiply by 5 degrees Celsius, divide by 9 degrees Fahrenheit. Again, I am canceling these Fahrenheit units, and I see that 73.4 degrees Fahrenheit is equal to 23.0 degrees Celsius. To convert from Celsius to Fahrenheit, I have a different form of this equation, which you would get from just solving for degrees Fahrenheit in that other equation, where the degrees in Fahrenheit is going to equal the temperature in Celsius. First, we multiply by our conversion factor, 9/5, and then we add 32 to it. If we look at an example here, we have a hot cup of coffee, has a temperature of 94.3 degrees Celsius. What is the temperature of the coffee in degrees Fahrenheit? So we start off by having our value in Celsius here, 94.3. We multiply it by 9 degrees Fahrenheit for every 5 degrees Celsius. We've canceled the degrees Celsius now. I can simplify that down after I've done that math to 169.74 degrees Fahrenheit plus 32 degrees Fahrenheit, and I can see that the temperature in Fahrenheit is 201.74 degrees Fahrenheit. And this kind of checks out if we think about it intuitively, because water is going to boil at 100 degrees Celsius. So this is a little under that value there. And it's going to boil at 212 degrees Fahrenheit. And this is a little under that value as well. So a little sanity check there at the end. So there's another temperature scale that you guys may be less familiar with because we don't typically use it, where Celsius is used by most of the world and Fahrenheit is used here in America. We also have the Kelvin scale, which is named after a very famous chemist who was able to determine what the coldest temperature possible is. Okay, and he set up this scale where 0 Kelvin is the absolute coldest temperature that anything could ever be, and it just happens to be negative 273.15 Celsius. And then he also set it up so that each one of the Kelvin units is going to be equal to a unit of Celsius. So it actually makes this conversion between Celsius and Kelvin pretty straightforward. I'm not going to show you how to convert to Kelvin from Fahrenheit. I'm instead going to suggest that you take the Fahrenheit value, convert it to Celsius, and then convert that Celsius value to Kelvin. And so the conversion, like I said, is pretty straightforward. To get the temperature in Kelvin, you're going to take the temperature in degrees Celsius, and you're going to add 273.15. So let's look at an example of this. The temperature inside a refrigerator is 4.37 degrees Celsius. What is the temperature of the refrigerator in Kelvin? So what we're going to do here is we're going to have 4.37 degrees Celsius plus 273.15 degrees Celsius. I'm going to write this conversion factor here just to show you how the units work out. But typically people are pretty lazy, so you don't see the conversion factor written up there because it is 1 divided by 1. It's not going to change the value. People often omit it, but it is there, and that is what's going to get us the cancellation of units that's going to get us into units of Kelvin. So if I do this math aside the parentheses here, I get 277.52 degrees Celsius. I then multiply by this conversion factor that is just multiply by 1, divide by 1. It's not going to change the value, but it's going to allow me to cancel the degrees Celsius and get into Kelvin. And I can see that my answer is 277.52 Kelvin. Okay, so far we've been talking about actual temperature measurements, points and measurements in temperature. And now we're going to switch gears a little bit to something a little bit more esoteric, a little bit more conceptual, where we're going to talk about the quantities that are just changes in temperature. So in this scenario, I start with a measurement of the final condition of my system. I could have heated it, I could have cooled it, but it's going to have a final temperature. And then it started out at some temperature. It has an initial temperature here. And then I'm going to define the change in temperature, which we usually write changes with these capital deltas, these triangles here. That means the change in something. It's usually always some sort of subtraction. Okay, so I have the change in temperature here, and that's going to equal the final temperature minus the initial temperature. And I will make that a little bit more bold so that you can see that. And it's important to get this order correct, that it's always going to be the final temperature, the last temperature where the system ended up at, minus the initial temperature where it started. So let's look at an example here. When heated in a microwave, a cup of tea is heated from 68 degrees Fahrenheit to 195 degrees Fahrenheit. How many degrees was the tea heated? So in this case, we're heating it and its final temperature is 195 degrees Fahrenheit. And its initial temperature when we put it in there was 68 degrees Fahrenheit. So my final temperature starts here at 195 degrees Fahrenheit minus 68 degrees Fahrenheit. And we can see that it was heated to 127 degrees Fahrenheit. So an important thing to note here is that we heated it. So the final temperature was higher than the initial temperature, and therefore delta T wound up being a positive value. we could easily have rewritten this question to be about cooling, right? Like I took a hot cup of tea out of the microwave. It was at 195 degrees Fahrenheit. I set it on the counter. It cools to room temperature, 68 degrees Fahrenheit, in which case the final temperature would be 68 degrees Fahrenheit. The initial temperature was 195. These two would have been reversed, and delta T would have been negative 127 degrees Fahrenheit. So our changes in temperature can just as easily be negative as well as positive values. Now, it turns out that when we're talking about the changes in temperature, our conversions between units actually get a little bit easier because we have cancellation when we do this subtraction. So in order to go from degrees Fahrenheit to degrees Celsius, we can just multiply by our conversion factor of 5/9. We don't have to mess around with that 32 value. In order to go from Celsius to Fahrenheit, again, we just multiply by a conversion factor. This time it's 9 degrees Fahrenheit for every 5 degrees Celsius. We're canceling those units. And we get our degrees Fahrenheit. And to go from Celsius to Kelvin, those are actually the same in this case, because the unit of a degree Celsius is the same size as the units in Kelvin. So I kind of jammed this example in here at the end, but I want you guys to kind of try and follow me. So if I asked you what this change in temperature up here was in degrees Celsius, you could think about doing this two different ways. You could first think about just changing this to degrees Celsius and then changing this to degrees Celsius and then doing the subtraction, or you could convert it using this formula I've given you down here. So let's look at these two different ways. So if I take 195, I subtract 32, I multiply it by our conversion factor, I see that that is equal to 90.6 degrees Celsius. I take the 68 value, I do the conversion for that, I see that that is equal to 20 degrees Celsius. I do our final temperature of 90.6 degrees Celsius, our conclusion from here. I subtract out the initial temperature of 20 degrees Celsius, that's from there. And I see that the temperature rose 71 degrees Celsius. This is a 3-step problem, but I could have just done it using this conversion factor up here. Let's see how that works. So I've already drawn the conclusion that delta T is 127 degrees Fahrenheit. I multiply it by 5 degrees Celsius for every 9 degrees Fahrenheit, and I get the exact same value of 71 degrees Celsius. So either way that you're comfortable with, I would argue that this is a little bit longer to go through than this, but both methods would get you to the correct answer, and it wouldn't be wrong to do it one way over the other, whatever you're more comfortable with.